Good morning. This is your flipped classroom lesson on atoms, and what you're looking at right now is Democritus. And he was a philosopher back in 400 BC that came up with the concept of what an atom was. And the way he came up with this was pretty simple logical thinking. He proposed that if you have a substance and you cut it in half, and then you cut it in half again, and again, and again, and again, and again, pretty soon you would get to a substance so tiny that it could not be divided. And that was his concept of an atom. And he was actually fairly accurate for that period in time in history of coming up with this. Now we can divide an atom now with the technology we have, but that took a while to figure out. So this is where the history of the theory of the atomic model came to be, starting off with Democritus. So next we have Dalton. And Dalton was a scientist in the early 1800s, and he came up with the atomic theory. And he had 5 concepts that his theory revolved around. And they're listed here, and we'll briefly talk about them. The first one is that all matter is composed of extremely small particles called atoms. And we know this, that everything in the universe is made of atoms, whether it's parts to your body, air, solids, gases, liquids, everything's made of atoms. He also proposed that an atom of a specific element are identical in size, mass, and other properties. And what this means is that if you have 2 atoms of aluminum, they're identical to each other because they're both aluminum. But yet they're different from other types of elements. So an atom of aluminum has some differences if you compare it to an atom of lead. So that's what his second statement said. His third statement is partially true. He thought that atoms could not be divided, which we now know how to do that. That's nuclear physics. But he was correct in stating that they can't be created or destroyed. So you can't create atoms, you can't destroy atoms. Atoms of a different element combine to form compounds. And he came up with this theory, and he talked about that they form in specific ratios. So for example, you have H2O, and so that's the compound water made by hydrogen and oxygen, 2 parts hydrogen, 1 part oxygen, and that's the whole ratio component to it. And then the last thing in his theory was that these atoms, when they undergo chemical reactions, can be rearranged, broken apart from one another, and rearranged in different combinations to form different types of compounds. So you're looking here at the history of the timeline of how an atom evolved through time, the idea of what an atom looked like and the parts to it, how it changed through time. At first, we already talked about Dalton and Democritus, and they basically just thought that an atom was a particle. They had no idea of what it might have been composed of at the times. But in the late 1800s, Thomson discovered that atoms are positively charged, and he also discovered that they have negatively charged parts to them. And this is where we came up with the proton positive and the electron is negative. Now he thought, they call this the cookie dough model, because Thomson thought that the entire atom was sort of a positive charge, but all the electrons that were inside of it, almost like chocolate chips and cookie dough, were negative, and that they balance each other out to make a neutrally charged atom. Later, in 1912, a scientist by the name of Rutherford discovered the nucleus, and that the nucleus is the center of the atom, and he didn't know that there were neutrons yet, but he knew that the nucleus was positively charged, and he also discovered that the electrons spin around the nucleus instead of being stuck in it like chocolate chips in Thomson's model. And then, shortly after that, Bohr, a year later, discovered energy levels. And he theorized that the atom's electrons actually spin around the nucleus in different orbital paths, almost like a solar system where the sun is the nucleus and the different orbital paths of the planets would be the electrons. Some are closer to the nucleus, some are further away. And so this was similar to Rutherford's theory, but a little bit different with the different energy levels. And then the current day model, the neutrons were eventually discovered to be part of the nucleus, and the current day model is called the electron cloud model. And that's a concept of what an atom might really look like, that the electrons spin around so fast that you can't really see where they are at any one point, so it looks like a cloud. I kind of think of this like when you look at a ceiling fan, it just looks like a blur, even though it has individual blades. So this is the history of the atomic model, and you're going to need to know the order in which these discoveries occurred in time, sequence-wise. Just real quick, this is the experiment that Thomson used to discover the proton and electron. He actually had negatively charged and positively charged metal plates, and when he proposed that a beam would go right through the center, but he observed that the beam was bent, and this bending was because of the opposite charges either attracting each other or repelling each other. So this is the experiment that discovered the protons and electrons. Now this was Rutherford's famous gold foil experiment that discovered the nucleus. It's quite interesting. So he had a beam that he shot through a very, very thin piece of gold foil. And he proposed that atoms are mostly made up of empty space. And he said if they're mostly made up of empty space, then these beams should just go right through the foil and not be deflected at all. And that was his hypothesis. And so this is what he thought was going to happen here. That the beams, which are the black arrows, would just go right through the atom and not be deflected or anything because the atom is mostly empty space. Now what he observed was that the beams actually were deflected at pretty large angles. And he didn't expect this. And so he proposed that there must be some solid part to the atom in the center that is deflecting these beams. And that's the discovery of the nucleus. So now we know the nucleus is the center, and it is a massive, solid, dense part of the atom, but most of the atom outside of that is empty space. So let's talk about the parts of the atom. This is a picture of what we call the Bohr model, and it shows the different energy levels and the nucleus in the middle. And we need to learn the parts and where they're located. Now, most atoms are neutrally charged, and we'll talk about that, and that's because they have an electron and a proton. And the electron is negatively charged and the proton is positively charged. Now typically most atoms have the same number of electrons as protons, and so those opposite charges cancel each other out, and the atom is neutrally charged. And that's why it took a while to discover the charged particles, and actually that's why it took a while to discover what we call neutrons, because neutrons are the third particle in an atom, and they have no charge. So think of neutral, no charge. Now we need to talk about the mass of these particles. That's important. The proton and neutron have identical masses, and their mass is what we call one atomic mass unit. And that's the unit for it, atomic mass unit. It's just very tiny. So the mass of a proton is equal to the mass of a neutron. And electrons have no mass. They are just little balls of energy with a negative charge. It would take like a couple thousand electrons to equal the mass of one proton, so we just say that they basically have no mass. So you're looking at the model here, and you can see the nucleus is in the center of the atom, and that's where the neutrons and protons are. So the nucleus is very dense. It has a positive charge because of the protons, and the neutrons and protons stick together with a force that's called the strong force, and we don't know much about that, but that's what the scientists call it. Now the electrons orbit the nucleus in different energy levels, and there's some rules about how many electrons can exist in different energy levels, and the rule is only 2 electrons can exist in the first energy level. The second energy level can hold up to 8, and beyond that, third energy level can hold more, but then the rules kind of change. There's no like real pattern to it that's obvious anyways. So you're going to need to know the parts of the atom: electron, proton, and neutron. You're going to need to know the charges. Electron's negative, proton is positive, neutron's neutral. You're going to need to know, and this is important, that the mass of a proton and a neutron are equal and are one atomic mass unit, and that the electron has no mass. Okay, now we're going to practice diagramming an atom. That's what I want to teach you in this lesson more than anything. So let's look at the next slide. Okay, so here is one of the elements on the periodic table, and we're not going to study the whole table today. We're just going to look at one box, one element in the periodic table, and understand what the numbers mean in that box. Now, this is boron, and B is the symbol for boron. And what you need to learn how to do to understand atoms at a higher level is understand the structure of them, what they're composed of, and where the electrons are, and the energy levels. That's the most important part. So we're going to draw what we call a Bohr model. And you're going to have to do this in class in a lab, so you're going to want to pay attention very closely. And the first thing we look at is the atomic number. And that's the number above the symbol. Every single element has an atomic number above the symbol. And for boron, it's 5. And what that means that there are 5 protons. I'm going to put P+. And it also means in a neutral atom that there's 5 electrons. And I'm going to put E-. So that atomic number is important. It tells me really simply that there's 5 protons, 5 electrons. Boom. The more difficult part is the atomic mass. Now remember, I said that the only particles that have mass are protons and neutrons, and they have an atomic mass unit of 1. Now this is not a whole number, it's a decimal, and you'll learn why it's a decimal later. But for now, let's just know that we have to round this to the nearest whole number. So 10.81 would round to 11. And so the atomic mass of boron, we can say, is 11 AMUs, atomic mass units. Now, here's the question. You can figure out using some simple math. If we know that there's 5 protons, and the atomic mass is 11, and we know that neutrons and protons have the same mass, then you should be able to figure out with a simple math equation how many neutrons there are. So if there are 5 protons, but the total mass is 11, then there must be 6 neutrons. And that's how we figure that out. So the sum of protons and neutrons equals the atomic mass. So when you diagram this, here's what it's going to look like. You're going to draw a nucleus, which is a circle, and you're going to put a little p and a little n in there. Instead of drawing dots, we're going to put the letters, and we're going to put the number of protons and the number of neutrons in there. Then you can draw a dotted line for the energy levels. Okay? So remember, the nucleus is where the protons and neutrons are, and the nucleus's mass, that's where all the mass of the atom is. Right now it's 11, and that's because there's 5 protons and 6 neutrons, and 5 plus 6 is 11. And here's our energy level, right here. Okay? And we're going to draw in the electrons. We'll do that with red. Now, we know there's 5 electrons, and I told you earlier that only 2 electrons can go in the first energy level, and then it's considered full. After that, you get a second energy level. So we're going to draw that second energy level, and we have 3 more electrons to draw in, and the electrons in the second energy level can hold up to 8, so we certainly have room for those 3 more electrons. And so this is our atomic model of boron. You can see the nucleus, 5 protons, 6 electrons. We get the 5 from the atomic number, 5 protons. And we get the 6 neutrons because we know that if there's 5 protons and the mass is 11, that there must be 6 neutrons. So the sum of the nucleus, the sum of the particles of the nucleus must equal the atomic mass. And then we know there's 5 electrons from the atomic number. And the atom's neutral because the 5 protons are positively charged. They cancel out the negative electrons. And so we know that there are 5 electrons. 1, 2, 3, 4, 5. 2 in the first, 3 in the second. And remember, the second fills up at 8, and then the third energy level would begin to fill up if there were more electrons. So here you go. You're going to have to do this in class, so if you need to watch it again, watch it again. Hope you enjoyed it.